we have seen that we can map the problem of vibrations on a string, on a one-dimensional string, when we quantize it to a problem of particles that are bosonic particles, and they're called phonons, and they represent the modes and are the true degrees of freedom of this problem. So we started from Lagrangian, that was some function of displacement field phi and its time derivative and the space derivative. Actually, it was just a function of the derivatives, and we essentially mapped it into a quantum Hamiltonian that can be written as a sum over k and h bar omega k, ak dagger ak plus a half. So it's describing a set of degrees of freedom that behave like a simple harmonic oscillator, and these operators, A and A dagger, are creation and annihilation operators for phonon at mode k. And the modes are completely separable from each other. So for each k, we can find eigenstates and eigenenergies independently, and the Hamiltonian is just a simple sum of them. And the A and the A dagger are related to the Fourier transforms of phi k, and the conjugate momenta pi of k, and they obey the commutators that ak prime dagger is a delta of k and k prime. So for k different from k prime, they are commuting, but for the same k, they obey this commutation relation, and this is okay, and this is consistent with the canonical commutators of the original variables, which were coordinates and momenta of the particles on the string. So this simple model showed how we map a problem of strong interactions between particles to a system of independent particles, but the new particles are collective things in terms of the original coordinates and momenta. We also noticed that the Hamiltonian has very simple expression in terms of the A and A dagger, and the meaning of the operator A dagger A is a number operator. So when it is applied on a state that contains a well-defined number of particles from the mode K, it gives us an eigenumber, which is just the number. It just counts the number of particles with that wave vector. And if it's applied on a state that doesn't have a well-defined number of particles, it will give us something, but we know exactly what it does, because we know that the operator A dagger is a rising operator, so it always adds a particle, and A lowers a particle. And in fact, we can do all the quantum mechanics using this language. And our quantum states are going to be the most general quantum state of this system is characterized by the occupation of different K modes. And we can explicitly write it in terms of the creation operators as a product of all the possible K, 1 over square root factorial of K, AK dagger to the power nk, all that acting on the vacuum. So there is a vacuum, which is the ground state. The vacuum is the ground state. It has, it's by definition a state with zero occupation of bosons in all the states. And each time we apply a creation operator on the vacuum, we create more and more particles. And if we apply it nk times, we create nk bosons in each k, in state k. And this is the most general, well, it's not the most general, it's a set of states from which we can we can use as a basis to describe all the possible quantum states. So there is a Hilbert space that this kind of states can describe, fully describe it, okay? And it has a given energy, which we can easily get from this, by applying this Hamiltonian on such a state, we see that the application of AK dagger A, the number operator, on such a state will give us simply nk, the number of phonons in state k. Okay? And the sum of that with h bar omega k will give the total energy. Okay? So these are eigenstates of this Hamiltonian. Okay. Now I'm going to show you that in a different problem, which in which we wrote down the Lagrangian or the Hamiltonian from a completely different starting point, we can once again map it to such a Hamiltonian that has an extremely similar form. And the problem is the electromagnetism. Okay, so remember that we so far discussed two specific examples of quantum models where it is very convenient to write them in terms of some field theory, which describes Lagrangian density depending on some field. This example was the starting point was a microscopic system of particles connected by springs. So it was connected to some particle, some microscopic description. Another problem was the electromagnetism, where we concluded that then the starting point was that we knew the equation of motion, and we wanted to write something that gives the correct equation of motion, which is the Maxwell's equations. So in the problem of the electromagnetism, our starting point was to guess Lagrangian in terms of the vector potential, the 4 vector of potential, A, and then we got, we concluded that it has a very simple form that gives you the equations of motion, so all that we've seen. So now what I'm going to do is to quantize that theory and show you that a very similar mapping occurs. Okay? So this was for 1D vibrations in the string. Okay. And now the next problem is Electro-Magnetism. Okay. So let me write the Lagrangian density actually. This is we've seen that it can be written, assuming now for simplicity, I'm assuming that there are no there are no charges and no currents. So J mu is 0. Okay, so this is in a vacuum. And then the Lagrangian density is simply given as a quadratic expression of F mu nu, where F mu nu, where mu nu stand for the 4 indices of space and time, and F mu nu is defined as in terms of derivatives of the 4-vector potential A. Okay? And I also remind you that A, the 4-vector, it has the time component is the electrostatic potential, and the 3-vector potential together makes a 4-vector. Okay. Okay. So now you see that now when I plug in the derivatives, I'm going to have some time derivatives and space derivatives, and it's very similar to the theory for the vibrations on a string, except that it's more complicated. Why it's more complicated? Because here we had only one field, one scalar field, which is the displacement of the atom or the particle at point X. And we had only one space derivative because it was one-dimensional. Here, we have something more complicated because the field itself, the A, has several components, and we have also 3 space indices at one time. But nevertheless, we can choose a particular form of it, which gives a relatively simple Lagrangian. Now here I want to note that there are some additional funny thing about the electromagnetic field. The vector potential is not uniquely defined. As you remember, there is a gauge symmetry. Okay, and that gauge symmetry suggests that not only you can add a constant to A, but you can make a gauge transformation. So you can change A mu to A mu plus some derivative of a scalar function gamma, and there are infinitely many choices of gauge that give the same physical fields. Okay, and that gauge freedom is actually telling us that we will have a different form. Okay, we'll have a different form of A and therefore different form of the Lagrangian for different choices of gauge. However, and that is something that will give something that looks like there is an extra degree of freedom that is in fact fictitious. Okay, so changing the gauge is a symmetry, and there shouldn't be any degree of freedom related to it. I'm not going to spend much more time talking about it at the moment, but I'm actually going to use the gauge freedom, because having a freedom, and you've seen it many times also in your first year studies, you can use the gauge freedom to choose a convenient gauge, okay, for whatever is your purpose. Now, for our case, it turns out that a convenient gauge choice is the so-called Coulomb gauge. Oh, I'm sorry. Coulomb. So the Coulomb gauge is that phi, the electrostatic component, is 0, and the vector potential obeys that its divergence is 0. Okay, you're familiar with this? I'm sure you've seen it.
Coulomb gauge indicates phi equals 0 because, say, in electrostatics there is a potential in the space.
It doesn't have to be, because the electric field can be, it's generally a time derivative of A plus grad phi, or minus grad phi, right? So, yeah, so that's exactly the gauge choice. Okay, so having, for the same electric field, you can have no electrostatic component and just A, which is going, it has to be time dependent to generate an electric field. Okay? Great. So so let's use this gauge. And why is this gauge useful? Because now I'm going to use the next board. So within the Coulomb gauge, the Lagrangian density will now become something that is very much familiar to you. Okay, and notice that I'm now using units where the velocity of light is 1. Okay, so if we want to in the end that real physical quantities, we have to plug it in. So that's why the space and time derivative are appearing in the same way. Okay. So this is just what you get in the special case that I choose this gauge, and this form is very familiar, right? Because what is the first term?
Electric field square.
This is exactly the electric field square. And the second term is nothing but the magnetic field, right? The curl of A. So this is the Lagrangian density, and there's a minus sign because it's a Lagrangian, right? And if we convert it to Hamiltonian, it will look like the familiar energy of electromagnetic, yeah?
אני אשאל את זה בשביל סטטיסטיקה.
Yeah?
בעיקרון, בשביל להגיע לכל הפור וקטור וכל הדברים האלה, מה שאמרנו בשדות זה לעבוד עם קיול לורנץ ולא עם קיול קולומב. כאילו, אמרנו שזה לא יעזור לנו שם. אז למה זה עדיין עובד
Okay, so let me just translate it. The question was that in order to show that you got this form and all that, you assume the Lorentz gauge, right? But that's exactly the point. There is a gauge freedom. Okay, so it's not gauge. It's actually, I think in your homework there's a question, right, to show that this form is not gauge invariant, but okay, but you can okay, yeah.
Which form is in gauge invariant?
The f mu nu, f mu nu.
Ah, okay.
Okay, but yeah, so right, but okay. Now I mean, okay. Actually, perhaps this can be checked if there is, yeah.
But F consists of only real fields, electric and magnetic fields. How isn't it gauge invariant?
No, but no, it's not the F. F itself.
Yeah.
F itself, all the components are physical fields, but the question is about the form of the Lagrangian. Okay, but the difference between different choices of gauge is something that doesn't affect anything. Okay, so it doesn't have. It doesn't change the equation of motion as it should. So, okay, so we can work, yeah. We can work in this. This is just the simplest gauge that gives something you immediately recognize. Okay, so. So you notice that it's very similar in a sense to the harmonic vibrations on a string, in the sense that there is a term that is like a kinetic energy, right? And a term that is like potential energy. All right? And in particular, it has a term that has the time derivative of A, and therefore we can define just like we do in general. We can define momentum operator or momentum field by taking the derivative of the Lagrangian with respect to the time derivative of A. Okay, this will give us a momentum. Now, however, we don't want to work in this representation of real space, because just like in the case of the vibrations in a string, here we have a derivative in space. So it's not local. It's not local. Okay, it describes it's a curl here, but it's a space derivative, so it's better to go to a representation that is local, and that is once again going to be Fourier representation. But here we have to write, so we first, before we do the, we transform from Lagrangian to Hamiltonian, I want to go from A to A of x and t, or A of r. I want to change it to Fourier space. So let's write it like this. And I have to notice that A is now, it's a vector. It has 3 components. And it also depends on space that has 3 components. And let me just write down, okay, so let's write down normalized, sorry. Okay, so there's a 1 over square root of, here I think it was 4 pi, yeah, 4 pi. Omega is a volume. And then there is a sum over K of alpha K okay, so I did a Fourier transform on space. I moved from A of R to alpha of K.
What's the volume?
The volume of the system, okay, so which, you know, if you want to describe infinite volume, you take it to infinity, but usually to keep things regularized, you keep some normalization here, because if omega is finite, the values of k, notice that I wrote a sum here, the values of k are quantized in some way that obeys the boundary condition, and if it goes to infinity, we get an integral over k here instead, okay? Oh, good. So, and sorry, I forgot something important. So, of course, these are the alpha k's are vectors themselves. Okay, they are vectors in 3 dimensions. But notice that alpha, so they're vectors in 3 dimensions, and in principle we should write them as alpha x, alpha y, alpha z, but there is a constraint on what kind of directions they can take. And where does it come from? Remember how we got this? We got this form by assuming the Coulomb Gauge, which is that the divergence of A has to be 0. Okay? So this expression has to obey that. And the only way to obey it, if I apply the divergence on this expansion, I get that k for k times alpha has to be 0 for any k. Okay? Okay, so what does it mean? It means that for each k, I mean k itself can have any direction in the 3-dimensional space, but for any k, what can I say about the direction of the vector alpha? It has to be perpendicular, namely in 3 dimensions it has to have, it can have components only in the plane perpendicular to k. Okay? So it's a purely transverse vector field. And therefore, if it can have only 2, so because it has to be in a plane that is perpendicular to k, in that plane, it can be characterized only by 2 unit vectors, right? So for each k, we can choose 2 unit vectors that characterize the x and y direction in that plane. And these 2 unit vectors are called polarizations. Okay? So for each k, we get, we can express the alpha of k as sum over, let me call it lambda, not to confuse, okay, is that alpha, so lambda equals 1 and 2, alpha k lambda, epsilon k lambda, and epsilon k lambda are unit vectors that obey that epsilon k1 vector product with epsilon k2 is the unit vector in the direction of k. Okay? So that's a way to enforce the perpendicularity of alpha with respect to k. So we see that the vector alpha k can be replaced by two scalars, okay? Two scalars, alpha k1 and alpha k2, okay? So although it's although it's a three-dimensional space, we have only two polarizations. Okay, very good. So now we are ready to plug in this expansion in the Lagrangian and get a Lagrangian form in terms of the k modes. Okay, and the result that we get using this normalization, etc., is going to look something like that. So we have a sum over k and lambda. Okay. What I'm doing now is just to plug in this expansion into the Lagrangian, okay? And that's what you get. There's first time derivative and minus omega k square alpha k. Sorry, I have to make some more space. Alpha minus k and lambda. Okay, and omega k is in fact, in the units that I'm working with, is simply the absolute value of k. However, if we kept the velocity of light to be not equal 1, it will be multiplied by c. Okay? Yeah.
Can you repeat, please, what lambda represents?
So lambda, once again, lambda represents polarization. So A is a vector, okay? And each component, each Fourier component of the vector field is a vector in 3 dimensions. But because this vector must be perpendicular to the propagation direction, it can be represented in the plane perpendicular to that k. And that plane, you need 2 axes, right? 2 unit vectors to this one.
So we have.
And so alpha. So let's say you can call them x and y if you like. But because you choose a different frame, different axis frame for each k. Okay. So that's why I don't call them x and y. I call them 1 and 2. And there are some arbitrary orthogonal axes in real space. Okay? There are some arbitrary directions.
Orthogonal to their respective k.
And yeah, they are orthogonal with respect to k and also with respect to each other, if you want,
okay.
So that they span. Okay? So they also have to be perpendicular. They have to be, okay, actually, let me be a little more precise here. Also, they have to obey that this is 0, okay? Although actually it doesn't matter. It doesn't matter. You can choose them to be not orthogonal, but it's convenient, if you like, to choose them in this way. So this is required. This is a convenience, if you like. Okay? Because any vector in 2 dimensions you can represent in terms of 2 not collinear vectors, right? So this is what they are. So they are called polarizations, and the important thing to notice is that if I look at the Lagrangian density in terms of the fields alpha, so they have 2 indices, k vector and lambda. And for each index, I get a separate contribution, right? So once again, very much like in the oscillators on the string, I have a division. The Hamiltonian separates 2 independent contributions from different modes. But here the modes are characterized not only by the wavelength or the wave vector, but also by the polarization, okay? And that takes take care of all the possible degrees of freedom that I have. And in this basis, they are really independent, okay? So I can solve it for each k and lambda independent. Okay. Very good. So, actually, to be really precise, let me bring back the velocity. Which pi?
כשעברת לאלפא?
So I erased it, but the normalization was, it had a 4 pi here. Okay?
Okay.
Okay, and then when I take the square, it takes care of the 1 over, so then the 1 over 8 pi becomes just 1/2.
רגע, הוא 1 חלקי?
Yes, sorry, I just wrote it and erased. So A of R is 1 over square root of 4 pi omega. Okay, so, but in the Lagrangian I have the square of this.
כן, אבל אז כשאני מכפילה אותו זה צריך להיות לי פאי בריבוע בחוץ, לא?
No.
למה? במעלה בריבוע היא בריבוע.
It's 1 of the square root, okay?
נכון, אז הוא יהיה 1 חלקי פאי כפול 1 חלקי 8 פאי.
No.
אז מה נתעשי את החשבון? זה מה שאני עושה.
So you're saying maybe I had it wrong?
לא יודעת, אני פשוט לא הבנתי.
Wait. Actually, no, I think you are right. Sorry. It has to be in the numerator.
כן,
It has to be in the
אין לי בעיה לשים פאי 1, גם אופציה.
Yeah. Why I had it? Okay, I had it wrong in my notes, so thank you. Yeah. Yeah, that's right. Okay. Okay. Anyway, it's just chosen in such a way that I get rid of the pi's. The pi is also just a choice of units. Okay. Okay, very good. Settle? Good. Okay, so great. So let me just emphasize this result. This is already very nice because, in essence, it's not very different from what we had for the case of the phonons in a string. The only slight extension is that we have another index here, but it has exactly the same form. So, indeed, if I now go to the Hamiltonian, how do I go to Hamiltonian? What I have to do? Take the, first of all, I have to define a momentum. So let's define a momentum field pi of k lambda, which is the derivative of L with respect to alpha, alpha dot of the same k lambda. So because these are independent degrees of freedom, for each k and lambda, I can do this. And then I get the Hamiltonian, and the Hamiltonian has the following form. So you can write it as, okay, let me first write it in terms of the pi's and alphas. So it's 1/2 sum over k and lambda, pi k lambda, pi minus k lambda, plus now alpha, omega k square, alpha k lambda, and alpha minus k lambda. Okay? By the way, notice that here and here I have always pi of k and minus k. Why is that? Just exactly the same story we had with the oscillator, because the field alpha of x and also pi of x are real, their Fourier transforms obey that pi of k is the complex conjugate of pi minus k. Okay?
But we have. Oh, okay.
Okay? So, so you see that if you look at this Hamiltonian, it looks exactly the same as the Hamiltonian. I didn't write it here in terms of the phi and the pi, but it has exactly the same form as the Hamiltonian of the vibrations, right? Except what is different here is, if you remember the expression we had in last week, here you should have 1 over m, and here you should have a factor of m, the mass. But so it's like the same thing, but the mass equals 1. And the reason is very prosaic. We just use the fields that they don't have units of length, okay? They have such units that you get the same form, but m equal 1, okay? So it's exactly the same. It's exactly the same. And everything we did for the oscillators, we can do here. And in particular, we can switch from the pi and the alpha to A and A dagger. Okay? And the transformation will be exactly the same. So we're just copying it. Okay? Let's write it now. So let's define AK, lambda to be the square root of omega over 2h bar, and then it's alpha k lambda plus I over omega okay, actually here I can write omega k lambda, but it only depends on k, so let me leave it like this. And the pi minus k. Okay, so that's A, and the A dagger is, of course, so it's alpha minus k minus I omega k pi of k and lambda. Okay? It's exactly the same transformation. And the commutation relations obeyed by these fields when we quantize the alpha and the pi is that ak lambda, ak prime lambda prime dagger is a delta on both k prime and lambda. Okay? So once again, we get a new set of degrees of freedom or particle-like things that are represented by applying a creation operator on the vacuum, okay? Where the vacuum, let's say, is the real vacuum here, and they represent bosonic particles. And what are these particles? You already know them from a long time. These are the photons. Okay, these are the photons. They are particles. They have boson statistics. And in the vacuum, they also obey a dispersion relation, which is that omega is the speed of light times k. And as we discussed last week, if I multiply by h bar from both sides, I get the relation between energy and momentum, which is the relativistic momentum of a massless particle. Okay? So this is all you know, but here you see that we started actually from classical electromagnetism. We wrote it as a field, as a Lagrangian, and we quantized it by going into momentum and to Hamiltonian and transforming the momenta in coordinate, or the generalized coordinates alpha, into creation and annihilation operators. And not surprisingly, the Hamiltonian also looks the same. Okay, so the Hamiltonian for the, if this was the vibration, the phonon Hamiltonian, the Hamiltonian of the electromagnetic field is now given by a sum over k and lambda, h bar omega k, ak dagger ak lambda plus 1/2. Okay? So exactly the same form, except that we have one more index. Okay, that's all. Okay. Very good. So, so these were just examples. They were simple examples. And what did we learn from them is that there is another way to represent a quantum problem of many degrees of freedom by, in terms of a set of operators that create and annihilate states, and this description, this set of operators, allows us to describe everything we want to know about this system. So first of all, we can represent all the wave functions, all the possible quantum states, in terms of superpositions of states of this form. Okay, so they just we have occupation of certain quantum states, and we can represent the Hamiltonian in this language, and we can in fact represent any operator that describes something that is related to either the number of particles or describe a process where we transfer particles from one case state to another, okay? And we can represent interactions, we can represent a lot of things, and it gives us a very nice and compact way of describing a system of many particles. And what is particularly nice about it is that we have chosen a definition of the degrees of freedom, or a basis of states, in terms of which the Hamiltonian is a very simple form. It's just a sum of independent particles, and it does nothing but to count them. Okay? Okay, so we would like to be able to generalize this formalism to more complicated systems. Well, we really need it because in the examples I gave you so far, we could have solved it without it, in a sense, right? Because they were all simple models where they're just quadratic forms of gradients of the fields. The equation of motion is a simple differential equation, right? So we didn't really need it, but sometimes we want to look at more complicated problems, and then it becomes important. And in particular, what do we want to describe? We want to be able to describe systems where there are many particles, okay? And these particles may be interacting in some way. So just knowing the wave function of each single particle is not helpful. And in addition, we want to be able to describe systems where the number of particles is not well defined because it's open, particles can come in and out, they can annihilate and become radiation and vice versa. Okay, you know that we can create pairs from the vacuum by some gamma ray. We want to be able to describe all these things. Okay, and what you saw here is an example of a new language, which is called Second Quantization, for historic reason. I mean, it's not that it's a new quantum mechanics. It's the same quantum mechanics, but it's a different way of presenting it, of formulating it. And soon we are going to see that it's going to be very useful in describing systems of many particles. And to give you some idea of why we really want to develop this new, or to adapt this language to any system of many particles, let me give you an example of a situation where we have particles that are not interacting. Okay? There's no interaction. Even that is complicated when you want to solve the problem of many particles. Okay, so let's now assume that there is some quantum system where you have, let's say, some potential and kinetic energy, and you have many particles that are identical. And these identical particles can be either bosons or fermions. Okay? And now we solve the single particle Schrödinger equation, and we find that there is a states lambda. Now lambda represents something else. Okay? Lambda is some quantum number that describes the single particle. So this is a complete basis of states. It can be either R or K or the index N of harmonic oscillator, whatever. Okay? It's some quantum number, and it's a solution of the single particle Schrödinger equation with energy epsilon lambda. So this is a single particle state. A single particle state. And we can also write how the wave function of that state look in the real space basis. What is this? It's defined by the overlap of a state lambda with the state R. Okay, that's just a definition. And the states lambda are single particle states. But now I have two particles, two identical particles, and I want to write a wave function which describes, so let me call this wave function now psi of R1, R2. R1 and R2 are the coordinates of the two particles. And I want to write a wave function that describes the particles in either of the two states, lambda 1 and lambda 2. Okay, so imagine that I have just two levels, and I have identical particles. Okay, and I want to write a combined wave function that describes them in terms of the coordinates. Now, how will I write it? How it will look? Now, it depends what are the kind of particles. Are they fermions or bosons, right? What is the difference? Exactly. So the wave function has to be symmetric if they're bosons or anti-symmetric. But if I just write the product of phi lambda 1 R1, phi 2 lambda 2 R2, this is not going to be to obey this symmetry property. So what I have to do, I have to symmetrize or anti-symmetrize. In other words, the wave function will look like this. It will be something like R1 lambda 1, R2 lambda 2, plus or minus, depending on whether they are bosons or fermions, R1 lambda 2, R2 lambda 1. Right? Okay, great. And And another way, perhaps, to write this is I can write it as okay. I can represent psi lambda 1, lambda 2, R1, R2 as of lambda 1 cross sorry, write it like this, where lambda 1 and lambda 2 is 1 over square root 2. Let me write it like this, lambda 2 cross lambda 1. Okay, so this represents that lambda 1 will be at position, I mean, coordinate R1, and lambda 2 at coordinate R2, and zeta is -1 for fermions and +1 for bosons. Okay, so we are going to use this index a lot in the next classes. Okay. Okay, so here I wrote a wave function of 2 particles, and now if I can imagine some Hamiltonian that depends on the two coordinates, and I can solve a Schrödinger equation by applying it on this state and looking for solutions. But what will happen if I have not 2 particles, but n particles, where n is very large? I can do it, but I will get, how will the wave function look like in general? So I can write a wave function for, this is now for n particles. And once again, they are identical particles. So the state lambda 1, lambda 2, lambda 3, up to lambda n. And notice that I have some ordering of the particles, and I give quantum numbers to each particle. So how will it look like? So there is some normalization factor that is 1 over square root of n factorial, and then there is okay, there's another, actually there is another, sorry. Okay, there are two, this normalization factor is because I take into account all the permutations of n particles, and this normalization factor, because if they are identical particles, then if they are in the same state lambda, they are, can exchange any number I want. By the way, if they are fermions, n lambda can be at most 1, right? But if they're bosons, this will give me another normalization factor. And then what do I have? I have now a sum over permutations. So these are permutations of the particle and the state index, okay? And, okay, let me erase this. So I can write it as follows. It's 1 minus, sine of p over 2. And lambda, p lambda 1 cross p lambda 2 to p of lambda n. Okay? This is the full expression. What is the meaning of this? So imagine that it's just a generalization of what we had before. We choose some ordering of the particles in states lambda, with different lambdas. And I now perform a permutation. And this permutation will give me an odd, if it's odd, namely I have to turn it back odd number of times to get back to the original ordering. Then if these are fermions, I pick a minus sign. If they are bosons, it stays the same. Okay? So you see that here I have zeta, which is -1 for fermions and +1 for bosons. For fermions, if the permutation is odd, and by odd that means that the number of pairwise permutations is odd, okay? Then this is going to be 1, and then I get then I get 1 because a factor of 2, that's fine. And then it's a minus. Okay? And if p is 0, p is 0. Is that correct? Sorry.
-1. Shouldn't it be -1 in the power of p?
It should be -1. Yeah. Why is it written like this?
Sine of p, so it's either +1 or -1. It's even or odd. It's even permutation. 1 minus the sine of p is even, so it's zeta to the power of 0, which is 1.
Right.
So it's the sine of the permutation.
It's the sign of the permutation, right? So, no, fine, no, so it's okay. So it's okay, yeah. So if it's odd, the sign is -1, okay, and then it's 1 + 1 over 2, so it's zeta, 1 power of zeta. If it's 1, if it's odd, if it's even, then sign of p is 1, and we get 0. Okay.
Sorry, I didn't understand.
Okay.
The function sine is +1, -1, or
right.
0.
That's okay. So it's a bit confusing because we have.
The permutation is from 1 to infinity is +1. If it's negative, it's -1.
What do you mean by negative? So
minus 1 permutation. I don't know.
So the permutation. Okay.
The sine function.
Okay. So the sign, a permutation is defined as odd or even, depending of whether the number of pairwise permutation is. Okay.
I just don't understand the function sine. Sine used for any positive number. 1.
No. The sign of the permutation. The permutation is defined as. Actually, it's the parity. It's the sign of the parity of the permutation. Okay?
So it's a -1 in the power of p.
So okay, it's defined in such a way that the sign of p sign of P is -1 for odd and +1 for even.
So it's -1 in the power of P.
No, it appears that the zeta is, okay, it's zeta to the power 1 minus sine P over 2. It appears in the power, okay?
Okay.
So, in other words, according to this definition, this is either 1
Zero.
or 0.
That's okay. That's
Okay?
I'll talk to you about it later.
Okay, I still don't see what's the confusion. But, okay.
אני לא מבינה כל כך מה הכוונה בפרמוטציה, זה ההחלפה של חלקיקים בזה?
Okay, exactly. So let me explain what am I writing here? I imagine that I have my n particle and I put the first particle in lambda 1 and the second particle in lambda 2. Okay? Now I make a permutation that, for example, keeps everything fixed and exchange only lambda 1 and lambda 2, like I did before. Okay? So this is odd. This is an odd permutation. But I can have a permutation where I exchange this and then this and this. Okay? And by doing so, I'm going to move lambda 1 to the third place. Okay? But then the number of operations that I did is going to be even. Okay? And therefore, the parity of that permutation is +1. Okay? Okay? It's even. Okay? Okay. Now, and actually we are now spending a lot of time on just how to write the wave function. And you see that it's not very pleasant at all, right? You agree that, okay. Even if we now get rid of our confusion, and okay, it's just, especially when it becomes a large number of particles, so the number of permutations, of course, is growing very fast. And if I want to write it in terms of, let's say I'm now taking the overlap with some space wave function, R1, R2, etc. I want to write a wave function, a function of n variables, okay, which describes the total wave function, and it's going to be a sum of many, many terms, right? And that wave function is, okay, I want to see how some operators apply on it, and what kind of, if I have some operator and I want to calculate an expectation value in that function, it's going to be an ugly calculation. You agree? Okay. By the way, you can convince yourself that for fermions, because these n lambdas are just 1, this expression is going to give us the Slater determinant. Okay, so it's basically a determinant of all the permutations, right, of single particle wave function. It's very, and once again, it's not pleasant. So this is the first quantized representation of many particles. And however, what is the information encoded in this wave function that we really need? The information is, first, whether there are bosons or fermions. Second, what are the bases of single particle states? And third, how many occupy each state? That's all. And for that, we don't need this. We can write it in a different language by, if we can define operators that are creation operators of a particle at state lambda, then by applying these operators on a vacuum, we can get this state, and we can write it in a much more pleasant form. But of course, these operators have to obey some rules for this to be equivalent. Okay, so, and this is going to be called the second quantization. So, so the idea is the following. We need to know the following details. Sorry, let me write it from here first. Bosons versus fermions. Okay, there are only two species, at least in the elementary world. Second, we want to be able to describe the system in some basis of single particle states. And these single particle states can be associated with some energy levels. So there is some spectrum, single particle spectrum. And then what we need to know is what is the occupation of the particles in that state. Okay? And the wave function that we wrote here encodes this property, but instead of writing it like a sum of horrendous number of terms, I want to write it in the following way. So I want to represent it okay. Now, actually, okay, let me not, in order not to confuse, I'm not writing equality here because the indices here mean something else. Okay, so let's first see what do they mean here. What do they mean here? They mean the index of a particle. Okay, so the particle 1 I put in lambda 1, particle 2 in lambda 2. Here, I don't keep track of the index of a particle because they are the identical particles, right? So what I keep track of is the quantum numbers. So I have some hierarchy of quantum numbers which I choose arbitrarily or according to the spectrum. So it makes sense to start from the lowest energy. Like we have epsilon lambda 1, epsilon lambda 2. This is the energy spectrum. Okay, so we order them by energies or by some way, doesn't matter. And then I'm writing here an expression which tells me in this state I have one particle, here I have two, here I have three, etc. Okay, so. And here, actually, how many stuff I can have? As many as I like, because if they are bosons, and I have even actually, even if they are fermions, but I have infinitely many states, I can have infinitely many terms here, but it's well defined, okay? So let's take a specific example. Suppose I have this spectrum, okay, corresponding to lambda 1, lambda 2, and lambda 3, okay? And, okay, I have some more levels, and that's it. And now I put in the first state I put 2 particles. Here I put 1, and here I put 4. So how will I write this state?
סליחה, כשדיברת על הלמדה, התכוונת על חלקיקים שהם לא זהים. זה הכוונה?
No, sorry. Lambda, no, the part, so I have, once again, let me explain again. I have n identical particles.
Okay.
All of them are n, capital N, identical particles. Okay? But I have, in my spectrum or in my quantum numbers, I have a ladder of states. It's not necessarily a ladder, it's just a set of states. Okay, discrete states. Now, what I'm saying is that all the information I need to characterize the state is how many of my identical particles I put at each lambda. Okay? So, for example, lambda can be momentum. Okay, and I have quantized momentum. 2 pi over L, 4 pi over L, 6 pi over L.
אז הוקטור הזה הוא לא בהכרח בגודל n.
Exactly. Yeah, this vector is as it can be infinite because it can contain entries according to how many lambda states I have. Okay? Okay? So for example, if I want to represent the state described by this picture, how will it look? Okay, in this picture, I placed two particles at lambda 1, 1 particle at lambda 2, and 4 particles at lambda 3. So it will look like this. It will be 2, 1, 4. And then maybe something else. Some of them may be zeros. Okay? Maybe some states are not occupied, so I put 0. Okay? And now, because the particles are identical, it doesn't matter if I exchange any of the two. Okay? But the thing is that this state should somehow encode the fact that if I exchange 2 particles, or make an odd number of permutations among the identical particles, I should get a minus sign if they are bosons and a plus sign if they are bosons. A minus sign if they are fermions and plus sign if they are bosons. Okay? So, and there is a much simpler way to write it instead of using all these permutations. So, how do I do it? So, first of all, I define a vacuum. What is a vacuum? Is a special case of this state where all the occupations are 0. Okay, so there is a vacuum. Okay, that's the vacuum. Now, on this vacuum, I can apply an operator that creates a particle at a certain state lambda I. And if I want to generate this state that I just wrote, let me write it here. So I'm now erasing all this stuff. Okay, so it's going to be the product over all the possible lambdas of 1 over square root n lambda factorial a lambda dagger to the power n lambda acting on the vacuum. And now if I moreover claim that I have total number of particles is capital N, then when I write here the product over all lambdas, I have to put a constraint, which is that the sum of n lambda over all the lambdas should give me capital N. Okay? So this describes exactly the state that, in fact, I already erased. Okay? Which represents n, capital N, identical particles in at each lambda state I have a well-defined occupation, and the total occupation of all the particles is capital N. Okay? And in fact, if I don't want to impose this constraint because I'm allowing the state to have as many particles as I want, then I just erase this. Okay? All right. Now what I wrote here is, in fact, a set of states. It's not just one state. I can represent any many-body wave function I want in my system using superpositions of these states. In other words, it provides me a basis of states, and this is a basis for a Hilbert space that we call Fock space. So Fock space is a Hilbert space that in which any wave function, any many-body wave function can be written as a sum over occupations with some coefficients, okay, of this. And if I want to impose that this wave function describes capital N particles on this sum over all possible occupations, I have to add a constraint that the sum of lambda and lambda equals capital N. Okay? But if I want to describe a state that does not necessarily have capital N particles, but it can be a superposition of state with 1 particle, 2 particles, 17 particles, I can also write it in this form. I just have to erase the constraint. Okay? So this is a complete set of state, and it turns out to be a very convenient way of representing any many-body function, and later on we'll see that we can represent any operator that acts on this wave function in a simple way. So what are the building blocks of this theory? There are these 8 daggers, okay? And of course the conjugate, which are the annihilation of operators. But how do I know that we can do this? We saw examples, but these examples were for bosons. Okay, and the question is, so there is something here that looks funny. I'm claiming that I can use this language both for bosons and fermions, but then of course the 8 daggers have to be very different creatures in order for this to work for fermions, right? Okay, so after the break, we'll see how we do this. Okay, so this way of representing wave functions and operators is what we call them second quantization. Let's continue. So I just want one remark because there were some questions. When I write this notation, the number of entries here is in principle infinite because it's as many quantum states I have. But notice that if I have finite number of particles, then actually a lot of these entries will be just zero because the occupation is zero, and zero in a product when it appears in the exponent give you 1, right? So I have a product of infinitely many terms, but some or most of them are actually just 1, right? So it represents this set of states allowed me to have as many particles as I want, but as it's written, it has well-defined number of particles. Okay, good. So so now we have this problem that this seems like a very good basis of describing states with many particles, but first of all, they have to respect the symmetry or anti-symmetry of the wave function that we know has to be obeyed for identical particles. And we indeed had concrete examples how to express these operators in terms of some other fields that we started from, right? In both examples that I gave you, we found a concrete way of defining it. But I'm claiming that you don't need this relation. What you need is to define them in a way that will make the basis of states well defined, and will tell you what any operator that I write as combination of A and A daggers, I have to know how to apply it on some wave function and how to calculate expectation values. So so let's now write a more general definition of the operators A dagger. And of course, first we'll define A dagger, and then to be consistent, we'll have some concrete way of expressing the annihilation operator A. All right, so what I'm writing now is going to be actually a definition of the operator A dagger I. Now I will be an index that describes some quantum number. I don't want to call them lambdas anymore, just AI, okay? So how do I define an operator in a way that fully represents it? If I have some Hilbert space and I know how to write the most general state in that Hilbert space, then a definition of the operator will be what happens when we apply it on an arbitrary state in that basis. Okay? So let's see. We take a an arbitrary state in Fock space, which is given by this form, and we apply on it a creation operator of a particle in state I. Okay, now state I is somewhere somewhere here in the middle. Okay, so we have an Ni. Okay. Okay. So what I'm writing now is a definition. When AI dagger operates on such a state, I get the following thing, and here I'm writing an index zeta that I will explain soon, times zeta to the power Si. I will define everything soon. And now I'm writing N1, N2, N3, etc. And then in the place where I had Ni before, now I have one more particle, so it's Ni plus 1, and then everything else stays the same. So the only difference between this state and this state is that here I have one more particle at state I. Okay? Now, what are these things? So this is the state. So this describes a state with Ni plus 1 particles in state I, and it's related to this by some factor. Okay? Now, what is this factor? First of all, the zeta will keep all the time. The convention is -1 for fermions and +1 for bosons. Okay? This will be our convention. And what is SI? SI is the sum over J Okay, so it's counting how many particles I have in the states that are to the left of I in the hierarchy. So notice that I define here some hierarchy of states, which I number as 1, 2, 3, etc. I can do it by the spectrum or any way I like. It doesn't matter, actually, for any purpose. It doesn't matter, but notice that there is some arbitrariness. Okay, there is some arbitrariness in the choice. If I can give you a concrete example, suppose one of my quantum numbers is a spin, okay, and the states with spin up and down are degenerate. So what I put first, up or down, it doesn't matter. It will change this factor by a sign maybe, but it's just a global phase, if you like. So for any physical quantity that I define, it doesn't matter how I define the hierarchy, okay? So so that's the thing. Now, another thing that I have here to write a definition is what is Ni zeta. Okay, so if it's if zeta equals +1, namely for bosons, we know exactly what it is, right? This is just Ni. So let's first write zeta equal plus. bosons. It's just the occupation. Okay, so this is how I get the factor of square root.
That's for bosons, right?
This is for bosons. Here, this is my convention, okay? Or if you like bosons. But if zeta is -1, what it's going to be, you know that ni cannot be larger than 1. So we define it as ni, oh sorry, let me write it a little more spacious. It's going to be ni modulo 2. Ni modulo 2. So if it's, so in fact it's the, it's either 0 or 1. Every time we have an even number, it's giving us 0. Okay, and if it's 1, it's 1, and if it's 3, it's like 1. Okay? Modulo 2.
But then you get,
Yeah?
if there's already a particle, then you get 1 plus 1 modulo 2 is 1, so 1 plus 1 isn't 0.
You're right, but we are not, that's exactly the thing, we'll show it soon. So in fact, you cannot get anything that is larger than 1.
No, but it isn't 0. Well, you can.
Okay, so first of all, if this is a legitimate state for fermions, Ni, the original Ni, can be either 0 or 1.
Yeah.
Right?
Alright.
Now, if it's 0,
Okay.
then I get 1.
But if it's 1?
But if it's 1, I will get 0 because
Why?
Ni plus, because Ni sigma, Ni zeta
Is 1.
is, sorry,
That's why.
I have a mistake. Wait.
2 is 0.
No, sorry. Okay. Okay. Yeah. Okay. Sorry, that's. Okay, it's defined in such a way that no, you're completely right. It has so the whole thing has to be defined. Okay, so okay, so Ni to the power. So Ni. Sorry. Yeah. Sorry. Let me do it. Let me redo it. Okay, so let's put. Okay, leave it like this. So Ni zeta plus 1 is either Ni plus 1 or Ni plus 1 mod 2. Okay? That's the definition. Okay, so then there are no options. Okay? It's either 0 or 1. Yeah? Sorry? Yes, that's a definition of a creation operator. No. So I repeat, we have now a new language. Okay? We don't have the particles. These the particles are the quanta, are these things that are created when I apply this operator. They are the analog of the phonon, not of the harmonic oscillator. Okay? So this creates a particle in the state I. Or in fact, it raises the number of particles by 1. Okay? So it's defined in such a way that first of all, you see two things that differ between bosons and fermions. First of all, fermions from this definition cannot have occupation that is bigger than 1. Okay, so if we apply it on a state which is already occupied, we'll get 0, and if we apply it on an empty state, we create 1 fermion. Okay, so this is all legit. In addition, this factor can give us -1 or +1 depending on the parity of the number of particles. Okay? And as it stands, it's not that important, but if we look at, okay, we will see exactly what it does, but this is the thing that will ensure that we have the proper symmetry of the wave function. Okay? All right. Okay, so that's a definition. And now this is true for any state that I apply on it AI dagger. In particular, I can choose the left-hand side to be just a vacuum. So by applying by applying AI dagger on a vacuum, and the vacuum is just a state where everything is empty, I get 0, 0, 0, etc., and then 1. But then if on this I can apply Aj, and then create a particle at J, and then if it's a boson, I can apply Aj again. And I can, in fact, reproduce the entire Hilbert space by applying A daggers, okay? And I describe states with as many particles that I want, and because of this normalization factor, in the end I will get something that looks like that, okay? So this definition is consistent with what I wrote upstairs, okay? It's consistent with it, yes?
If you have two states, each has one particle, how do you know which to create first? Because you have that.
Very good, very good. So remember, we have to, so for boson and fermions, these operators are different. They have a different character, different algebraic character. Now, how do I enforce exactly what you asked? So, for example, I said I can first apply AI dagger and create, or I can, let's take a general state, okay? I apply AI dagger, I create a state where everything is unchanged except this I has another, one more particle. Now I apply Aj, and I will get, what will I get? I'll get, this state will now, will acquire, Nj will become Nj plus 1. But notice that this factor depends on the occupation at each stage, okay? Now I'm not going to do the algebra because this is exactly something you can do for yourself in the homework. But you can show that for a general, so let's first think of what will happen if I take two different states, I and J. Okay, so let's take two different states, and I'm taking a general, some general arbitrary state in my Fock space, and I look at AJ dagger AI dagger applied on this, and I can also exchange them and apply this on the same state, and then I get something. Okay, and then what you're going to show explicitly in a calculation is that A dagger, AJ dagger, applied on an arbitrary Fock state equals zeta AJ dagger AI dagger on the same state. Okay? Now let's how to move this to the left-hand side. Forgot how to say it in English. So the same thing can be expressed as this combination, AI dagger, AJ dagger minus zeta, where zeta is again the same zeta all the time, okay? Acting on the state, the arbitrary state, gives me 0. Now whatever is shown here is that there is an operator that is this particular combination of the creation operators that give me 0 when I apply it on any state in my Hilbert space, right? Therefore, what can I say about this operator?
It's a 0.
It's commutator, 0.
No, so any operator that gives me 0 expectation value in any state is 0, right? It's identically 0. Okay, I'm talking about the entire. So this is identically 0. Okay, and therefore I find an algebraic relation. Let me define now a generalized commutator A dagger I, A dagger J, with an index zeta. What I find from this is that it's 0. So the definition, let me first write so the definition is in fact that just this. Okay, if zeta is +1, which is a boson, it gives me a commutator. If zeta is -1, it gives me a so-called anti-commutator, exactly. So another way of writing it, which is probably more familiar, is AJ equal 0 for bosons and anti-commutator for fermions. Okay, well the anti-commutator is AI dagger AJ plus AJ dagger AI. Okay? So that's what I find for AI different from J. Okay? But now, let's see that what happens if I equals J.
But you still didn't answer my question. How do you know? I have two states. Each one has like one electron. How do you know which to apply first, which creation operator to apply first, because these are different operators.
I don't know.
A2, dagger, dagger.
What this tells me is that it matters. There are different states.
Exactly, so I'm asking, how do you know which one to apply, to use, to describe the system?
Okay, so we'll see about it later, how to express operators in terms of this. But it actually tells me when I write an operator in this basis, okay, when I write an operator in this basis, which describes my Hamiltonian, for example, will be a sum of operators. That's how we'll get to it later. We first work with the states, we define our building blocks, and then write the operators. But when I write an operator with a given order of application of the A daggers, it has a well-defined meaning, and I know that if I exchange them, I get minus that operator. Okay? Okay? So, either states or either application will give me a well-defined. Okay, once I stick to the original definition, I know exactly what it gives. Okay, but indeed, it gives me something else. It matters in what order I apply them. That's exactly right. Okay. So, which is exactly what fermions should do. It really encodes the property that I'm looking for, that any permutation changes the sign.
But it's permutation of states, not of...
No, it's a permutation of fermions. I mean, it's the it's the permutation of the occupation of the particles on the states. Okay? So it doesn't matter if you exchange the particles on the states, but you permute the association of particle to state. Okay? So, okay, so we showed that this is obeyed if I different from J. Now, let's see what happens when I equals J. And in fact, we'll see that it still holds, but we have to check. Okay, so okay, so let's look first on bosons. So what happens when I equals J? So I look at the combination I dagger J plus I J dagger, sorry, minus. This is the commutator now. But now I is equal to J, right? So this gives me nothing but AI squared minus AI squared, which is obviously 0. So this is trivially obeyed for bosons, okay? It's trivially obeyed. In fact, it just tells me that, you know, an operator always commutes with itself. Okay. But what about fermions? So let's calculate the following anti-commutator. And I'm writing it explicitly from the definition. What is the anti-commutator? It's AI dagger square plus AI dagger square.
You're doing now for boson the fermion what happens when I and J's are equal?
Yes. Okay. So what is this? And the answer is that it's also 0. Why? Because from the very definition of A dagger, if I apply AI, the same AI dagger twice, I get 0. And this happens when I apply it on any state. On any state, and therefore it's true identically. So the operator for fermions A square, A dagger square is 0. Okay? And therefore, the anti-commutator is also 0. So we conclude from it that this relation that AI dagger, AJ, the commutator for boson, the anti-commutator for fermions, has to be 0. That's correct for any I and J. Okay? So... Yes, that's actually, by defining the A dagger the way we define it, for fermions, it implies that I cannot occupy more than one in the same state. Okay? If I try to operate, I annihilate the state. Okay? It's identically 0. Okay? The double occupation is identically 0. Okay. Great. So, so now we know already that, let me write it in the compact way, that this generalized commutator is 0 for any I and J. Now let's apply the conjugation. So I still don't know exactly how to represent the conjugate of this, but I know that if I conjugate this relation, then the right-hand side will also have to be 0, right? So I can also say that AI and AJ, this is also 0, okay? And now to complete my algebra, what I need is to say something about A and A dagger, okay? But so far I only defined A dagger. So we are missing something. We have to define the annihilation operator in a consistent way. So first of all, there is already one definition of the annihilation. What is it? It's the conjugate of the creation. Okay? So however, I want to be able to describe it in terms of the states, as I did for the A dagger. Okay, so where shall I? Okay, let me write it right here.
How did you understand that for every I and J it's equal 0?
So once again, for I different from J,
okay.
I just proved it by doing this exercise that you'll do at home, okay? And what I proved, in fact, is that this combination of operators give me 0 on any state, okay?
We need like to.
That's when I different from J.
Then like we actually see it when we open the algebra.
Yes,
okay.
Yes, exactly. Just from the original definition.
Okay.
Okay? it follows from that. And then when I plug in I equals j, for bosons it's trivial because it's the same operator commutes with itself. For the fermions, I have to use the fact that from the beginning, I dagger square is 0. Okay, and that actually also follows from the original definition, right? Okay. So this I know, and now and I can also say that because it's just conjugating the operators or conjugating the equation. But now I want to see how to represent the annihilation operator in terms of what it does when it acts on the states, but it must be consistent with my original definition of a dagger. Okay? So once again, because I have a Hilbert space described by these Fock states, the only thing I have to show is what it does to a general state, and from this it all follows. Okay, so let's look at the following thing. I take the original equation upstairs that defines a dagger, and now I apply dagger on both sides. Okay, so the left-hand side gives me some state. Okay, but I can define the conjugate state, which is this, okay, with an I here, AI, okay, so this is nothing but the A dagger okay? So you're familiar with that state alpha dagger is this. Okay? Okay? Good. So this is just from the definition. And now I want to do the following. Let's see what is this. Yeah, so let's calculate the following thing. I want to calculate the matrix element between two arbitrary states. I put here AI, and I apply it here on N1, N2. Okay? And here I have, let me just be more specific, Ni prime, and here there is Ni. Okay? And I want to calculate the matrix element of the operator AI between two states. Okay? Now you agree that if I'm looking at, okay, let me use a color here. So this is nothing but the overlap between the state N1, N2, etc., to a state which is this. But what is this state? It's actually the conjugate of the state a dagger applied on the n prime and 2 prime, etc. Right? So this matrix element is the complex conjugate of n1, n2 sandwich with n1 prime, n2 prime. Okay? This complex conjugate. Okay, so let me repeat. What I have on the left-hand side is no longer an operator. Now it's a number. It's a matrix element. Okay, of the operator AI in between two arbitrary states in Fock space. All right, and I know it's a number. And if I conjugate everything, I get the complex conjugate of that number, okay? But actually, the right-hand side, I can easily calculate, right? Because for that, I can use the definition of the A dagger. So let's do that. Let's see what is this, okay? So I have to sandwich the n1, n2, ni with a dagger I acting on the prime. But what is ai acting on the n prime? It's going to give me just a number times the state with ni plus 1, right? So let's write what is this number. It's the ni zeta to the power 1/2, zeta to the power si. I'm just copying. And now I have n1 prime, n2 prime, etc. But ni prime plus 1. So here I use the definition of A dagger I, okay? Okay, but I know how to calculate this matrix element, right? How do I know? What is it? So first of all, this is just a number that I can take out. And notice that what can I say about this number? It's a real number. Okay, so the complex conjugate is itself. And then I'm left with the sandwich of the n prime and the n's. Okay? But because the states are orthogonal, right? I'm going to get, when I'm going to get the contribution that is non-zero, if n1 equal n1 prime, n2 equal n1 prime, etc., and ni equals ni prime plus 1. Okay? So the answer to this number is ni zeta plus 1 to the power half zeta to the power si times a delta of n1 prime times delta of ni and ni prime plus 1. Okay? Okay, so that's the matrix element, and it's real, and therefore its complex conjugate equals to itself. And therefore, I know to calculate a matrix element of the operator AI. Okay, so let me summarize what we got from here. I got that the matrix element to Ni plus 1 zeta to the power Si times delta product of all the delta functions, where the only thing that is different is that Ni has to be equal Ni prime plus 1. Okay. Okay, very good. So,
what's the difference between? יש הבדל ביניהם?
No, because that's exactly what I was going to say. So first, I showed this. This is given to the complex conjugate of something I can calculate. Okay. From what I already know, because I already have the definition of Heidegger. This something is a real number, okay? And therefore, it is also the matrix elements of AI when I compute it between the state with the Ni here and Ni, sorry, did I change? Sorry, I had a mistake. Sorry, this is. This is Ni. Sorry, that's just the original thing. Sorry. Okay. So I repeat. Sorry if I confused you. This is what I want to calculate. I'm using the fact that it's the complex conjugate of a matrix element I can calculate from the definition of Heidegger. I calculate this matrix element, and I find that because it's a real number, it's also the answer to this. Okay?
So the Ni is...
Yeah, so the Ni is, so the right hand, how do you call it, Brouwer-Ket, I never remember which one is which. So this one has Ni particles here, and on the left, Ni prime. Okay? Okay? So what I do here is to calculate a matrix element of the operator between two different states, and I get a well-defined answer. Okay? Yeah?
So the Ni plus 1 it's correct? I think it's something supposed to be different. It's supposed to be
let me see. Sorry. You are right. Okay, sorry. See, okay. Let's be more careful. You are right. Yeah. So this is all primes, including S prime. This is all prime because I applied this on the right. Okay? I applied it on the right, and I got everything is with prime here.
And in the... הדבר הסגול, זה נראה לי גם
in the purple frame.
And of course, this is the same. This is the same, right?
זה לא אמור להיות רק Ni? בלי Ni פלוס 1?
Well, no, so once again, okay, sorry, let's not get confused. So this is the thing I wanted to calculate, okay? But here I wrote it as a complex conjugate of something where here I apply the A dagger on a prime. Okay, application of A dagger on prime give me this number times a state with one more particle prime. Okay, so everywhere here I have to put the prime. This is just my mistake. Sorry about that. Okay. Now this is what is inside the brackets, which I have to conjugate, but conjugation is trivial because it's real. Okay? So therefore, I proved this equality. Okay? Well, here everything is with the prime. Okay? Okay, very good. But what is this? There is another way of looking at the same matrix element that I just calculated. There's another way to look at it, and maybe we should. Okay, let me erase it. Okay, so let's look at it like this. What we have here is, on one hand, I got it from conjugating and flipping back, but I can also look at it as the overlap between this state, okay, and this state. Right? Now, there is another thing that I can say. In the right-hand side, indeed, I have here n prime, but I have these delta functions. And therefore, this expression is non-zero only provided that there is some very simple relation between n1 and n prime, okay? So instead of looking at it as something that depends on n prime, I can use the delta function and rewrite it in terms of n, okay? So what do we have on the right-hand side? I have ni prime plus 1 squared, and I have si prime, but ni prime is nothing but ni minus 1, right? And therefore, I can replace this factor by ni to the power half. Another thing is, what is si prime? Si prime, so first of all, let me do this. So n prime is ni minus 1. And si prime is is the sum of all the occupations to the left of the site I. But the delta functions tell me that all the other occupations other than I are the same for the two states, right? So, in fact, n1 has to be n1 prime, n2 has to be n1 prime, etc. Okay? So, si prime is equal to si. Okay? This is correct because I enforce the delta functions. Okay? And because of that, I can say that, in fact, what is AI acting on N1, N2, Ni, it is equal to Ni to the power half times zeta Si times, what do I have to put here in order to get the delta functions correctly? It will be N1, N2, but this will be N1 minus 1, okay? And, אוקיי?
זה אין היה אבל של אתא, נכון? אז כאילו, אני צריכה להתחשב בזה שעם פרמיונים או בוזונים.
Yes, so the fact that it's fermion, the fact that it's fermion, actually this is, if you like, this is Ni zeta, okay, what I called, which is defined modulo 2 for fermions. But in this case, if from the start Ni, so this is in fact an annihilation operator, and from the start Ni couldn't be bigger than 2, than 1, right? So therefore, I don't even have to mention. Okay? So it has any meaning only if we have already an occupied state, and then we can annihilate it. Okay? For the creation operator, we had to be more careful. Okay, so the bottom line is we just proved that if that is the correct definition of a dagger, and if we define an annihilation operator to be the dagger of the dagger, then it must obey, when acting on any state in our Hilbert space, it must obey this equality, namely that it reduces the number of particles in state I and give me some prefactors. Okay? So let me summarize the rules here. What we found is that for any state in Fock space, I can apply the A dagger give me so it's a raising operator, and AI gives me Ni zeta Si Ni minus 1. Okay. And these two definitions are consistent, and they in fact tell me, because they tell me what these operators do for any state. They fully define the operators, and then I can ask myself, what happens if I apply a dagger and then A and then a dagger again, or any combination, okay? So now, what happens if I apply the annihilation operator on a state that has, let's say I have, okay, when I apply it on Ni, I get Ni minus 1. When I apply it on Ni minus 1, I get Ni minus 2 until, what happens if I apply it on 0 occupation? I get 0. Okay, so if it happens And you see it from here, right? So if Ni from the start was 0, that's true for bosons and fermions, I get 0. Okay, so a particular case of this is that acting on 0 in the position of the state I give me 0. And if I apply it on a state where if all the states were unoccupied, namely the vacuum. So the vacuum is a state where if I apply any annihilation operator, I get 0. Okay? Okay, so now I basically get all the building blocks of my theory. First, the vacuum obeys this, that any annihilation annihilates the vacuum. And the raising operator takes me from the vacuum and builds all the states in my Hilbert space. And the last thing we need is to complete the algebra. So we saw that the A dagger and the A dagger obey some commutators or anti-commutators, and the same for the conjugate. What am I missing here? What is the commutator or anti-commutator of A and A dagger, of either fermions or bosons? How do I do this? Another homework, okay? So now it's just algebra because we already have this. We can apply AI dagger and then apply AJ, and we can exchange them. And we can see what it gives. And just the same exercise we did before, we can see what the operator AI dagger AJ minus zeta AJ AI dagger, I can see what it does when I apply it on any state. Okay? And what it is going to give me, what do you think it will give me? Yeah?
What?
Delta
IJ.
Okay, right, exactly. So if so first of all, if I is different from J, it's going to give me 0. Okay? And if I equals J, it will give me 1 times the same state. So in fact, it will give me a delta IJ times the same state. Okay? And once again, that's correct for any state, and therefore it means that, okay, let me actually write it right here to complete the set. So AI, AJ dagger with index zeta equals delta
Shouldn't it be the opposite?
Okay, it doesn't matter. It doesn't matter. Okay.
Up to a minus sign.
Okay. Yeah, maybe. Yeah. Yeah. You're right. It's up to a minus. It's actually minus. But okay. Anyway, you see what? That's the correct answer. I exchanged them. Okay, so that's all. This is a complete set of algebra. I have two species of operators. They're conjugate to each other, and by using these commutators, I can actually see what any permutation does to any operator. So if I have a general operator of the form A alpha, A dagger, beta, A gamma dagger, something like that, we'll see, you know, what kind of physical quantities we can represent with such operators. Then any exchange will give me something which obeys these commutators, okay? So that's a set of states. We know that one is creation, one is annihilation. And we also know, and it actually follows from this directly. What is this operator? So this should be a number operator. In fact, for bosons, we already saw what it does. But also when we apply it on any Fock state, in the fermion case, it also gives me the same thing, okay? How shall we see it? So let's apply it on the most general fermion case. Now, fermions can occupy only one in a state, right? So the most general Fock state for fermions, this is for fermions. Okay? That's the most general state, fermion state I can write. Okay? And here I have a product of some lambdas. Okay? So, in fact, if you want to be a little more careful, so let's put here n lambda, but n lambda can be only 0 or 1. So it's a product of only the occupied states. Now what happens when I apply A dagger A on this? Okay, so in this combination I first apply A dagger, right? First apply A. But A is annihilation. So there are two possibilities. Either that AI was not occupied before, and then what happens if I apply it? I get 0. Okay? If it was occupied, I annihilate it. So I change Ni from 1 to 0. Okay? So, but then if I, okay, so AI dagger acting on AI gives me something non-zero only if I had, okay, I can write it like this, and if this is Ni, I get an empty state. Empty, okay. If okay, and now when I apply it once again, I recreate it. So in fact, I got back to exactly the same state, but with a factor 1. Okay? So this is a number operator for fermions. And for bosons, okay? It just conserves the number of particles. They give me the same state with a factor of Ni. So, yeah, so AI dagger AI is a number. When it acts on any Fock state, it gives me Ni times the same state, so it's these states with well-defined number of particles are eigenstates of the numbers. Okay, And we can also look at other types of operators. For example, what does this operator? Let's see, I want to erase something, so just change. So I have some operator that looks like this, where I is different from J. Okay? And I apply it on any Fock state. What does it do? Yeah, okay, it actually describes transition of a particle, a single particle, from state J to state I. Okay? So, for example, if let's think of a simple case that we have a two-level system for fermions, for example. So this is, and this is a spin half. So this is a spin flip operator. Okay? Etc., etc. So we can build all sorts of operators from this, and we can go on, but before we do that, notice that to start building the set of operators AI, I started by choosing some arbitrary basis of states. Okay, there's lambdas. And these lambdas were quantum numbers of the single particle. But now, of course, any basis, any complete basis is fine, is equally good. But sometimes the problem becomes simpler in the basis of momenta as opposed to coordinate, etc. We saw an example with the phonons, right? In order to be able to choose my basis the way I like it, depending on what is the problem I want to solve, we have to know how to do a change of basis. Okay, so let's do that. Will be the last thing for today. So okay, so that's a change of basis. Suppose I have a set of states lambda, or set of quantum numbers, and I want to switch to some other set that I call lambda 3. For example, this can be coordinates, and this can be wave vector. Okay, so first of all, let's define a resolution of identity. So if I look at the identity operator, I can write it in this basis as a sum over lambda. Okay, this is a resolution of identity in the basis of single particle states. Okay, provided that lambda is a complete basis, of course. And now I also know that if I want to represent the state in the new basis, lambda tilde, in terms of states of lambda, what I can do, I can introduce this resolution of identity and write it as, okay, so let me now do it explicitly, okay? But now, this is just a number, right? It's a matrix element. And so I can rewrite it as a sum over lambda, lambda twiddle, lambda. And these are coefficients, okay? So this is how you do change of basis from any basis to any. For example, if I have the state with well-defined coordinate, which is a delta function, I can represent it as a sum over k, and this is going to be I can represent it in terms of the k-vector basis, but what is this? This is the wave function in real space. Okay, which is e to the I k dot r, right? So this is, in this particular example, it's 1 over square root of the volume e to the I k dot r. Okay?
Not minus because you have
with a minus, yeah, because this is actually the conjugate. Okay, so it doesn't matter actually because we're summing over all k. So it's just a matter of definition. But this is the general expression. Now this is all first quantization, but now I want to use it to change basis for my creation and annihilation operators. So how do I do that? I simply use the fact that what is a single particle state? It's a special case of the Fock state, where I occupy only one state with one particle. Okay, it's a simple special case. So lambda is nothing but a lambda dagger acting on the vacuum. Okay? And similarly, of course, lambda twiddle will be a lambda twiddle acting on the vacuum. Okay? So now let us use this in the two sides of this equation. Okay? So in the left-hand side, I have lambda twiddle, which is a lambda twiddle dagger acting on the vacuum, and what I get is that that's equal to a sum over lambda of lambda twiddle times lambda, but lambda is a lambda dagger acting on the vacuum. All right? So in fact, what I find here is that there's an operator identity. In fact, if you like to be more rigorous, you can show that even if you apply it not on the vacuum but on any other state, it will give us the same. Okay?
How?
By induction. Okay, so in fact you can apply more and more A daggers, and you see that, okay, it works. So there is a simple way of switching from one basis to another. So let me write it like this. Lambda lambda twiddle A lambda dagger. And this is a change of basis. It's a simple linear transformation, in fact, for the creation operators. But I can get also similar thing. Once I know this, I can easily find the equation for the annihilation operator, because A lambda is going to be just a conjugate of the right-hand side. But what is the conjugate? It's a sum over lambda. Here I have to exchange lambda and lambda twiddle, right? Because it's complex conjugation. And this becomes A lambda. Okay? So that's a very general change of basis. And let's take a special case, which is the case that we're going to use a lot in physical problems that we're interested in. Let's change basis from R to K. Okay? So I'm defining now a field, a local field, a local creation operator, psi dagger of R. And notice that instead of A dagger, I write it as psi. Why? Because this is what people do in a lot of the literature. It's just a convention. I could write it as A dagger of R, but notice that the way I define it, psi dagger actually has dimensions. Okay? So what it describes is the creation operator for a particle located exactly at the point R. Okay? So what will be psi dagger psi on the same R? It's going to be the number of particles exactly at the point. Okay, but that's because it's a zero. Okay, it's at the point. So in fact, if you define the psi with dimensions that are 1 over square root of length, this will become density and not number. Okay. So okay. So if we define it. Just applying exactly the formula I used here, it's the sum over K, phi K of R, AK dagger, where phi K is 1 over square root of the volume, e to the I k dot r. Okay? So this function has dimensions of 1 over square root volume. Okay? And that's why when I take the psi dagger psi, I will get a factor of 1 over volume. And it has dimensions of density. Okay? So this is a way to represent a local creation operator in terms of creation operators of particle at wave vector k. Okay. Now remember that in the original basis the A. Okay. Let me just to finish it. I'll write the inverse transformation going from K to R is that A K dagger is going to be integral. Okay, the integral is whatever is the volume times this phi k of r psi. Okay? And you see that here, because this has dimensions of 1 over square root volume, and this as well, you get a dimensionless thing. Okay? So that's the inverse. So in fact, this is just a Fourier transform. Okay? And yeah, so what about the commutators? When I change from lambda to lambda twiddle? So of course, the A lambda twiddle, we expect them to obey the same algebra, right? And because they are, because of the transformation from one basis to another is a unitary transformation, right? From one complete basis to another complete basis. If this is obeyed, then the commutators are preserved. Okay, so if these are four distinct orthonormal bases, like the Fourier basis, then the same commutators are obeyed. So the delta is the same delta on basis. Okay, and what about these local operators? So if the AK and AK prime dagger are delta, okay? And now if I express them in terms of the psi's, or vice versa, if I express the psi and the psi dagger in terms of the A and the A dagger, what will I get? Okay, if you do the algebra, it's easy to see that you are going to get that psi of R, psi dagger of R prime is a delta. Okay, so this is the Dirac delta, not the Kronecker. And that's okay because the dimensions are right. This is dimensions of 1 over length. Okay? So, I think you're already tired, so this will be enough for today. No? We can go on for another round. So, yeah, let's... No, you can ask last question. Yeah.
פסאי, לא תלוי ב-K במקרה הזה בכלל?
Sorry? So...
בקומוטטור.
No, psi, so again, once again, psi can be expanded in terms of, psi dagger can be expanded in terms of AK dagger. Now, if I conjugate this, psi is just a conjugate of psi dagger.
זהו, אז לא חסר איזה קוסינוס או משהו של K מינוס K תג?
No, why? So, psi, so if this is the equation for psi, then what will be the expansion for, what will be the expansion of psi? What will be the expansion of psi? It's just what I did before. It's just the conjugate, right? So it's sum of okay. Okay? So, right, yeah. We just finish AK. That's all, right? So, and therefore, if I'm looking at this commutator, I get, and I use the Kronecker delta for the K and K prime, I get a delta function on R and R. Okay? Okay, it's very good. So next week we are going to see how we use this language to express various kinds of operators, physical operators, and how to take their expectation values and use the algebra to calculate this. Okay, thank you.